Right. See, this is a different and advanced question. Advanced question. Okay. We are doing preparation methods. Okay. By covering rearrangement, by covering ring expansion concepts, and this is another model question. In this we use resonance application. Right. Now I'm asking you one question. To which carbon Cl negative will be added? To which carbon Cl negative will be added? Clear? To first carbon Cl negative will be added. Okay. Any others? What is the mechanism? Yesterday I explained about mechanism, right? First we have to add H plus, right, and we have to check the carbocation stability. Based on that carbocation stability, we will do the rearrangement also. Clear? Let us go with the mechanism. First of all, I'll give the product for this. See, the product Cl will be added at a second carbon. At second carbon. Look at this. And H will be added at the first carbon. Clear? Let us check the mechanism. Why Cl is adding at the second carbon? Why not at the first carbon? Right. In this question we use resonance application. Okay. Look at this. What is the first step in the mechanism, electrophilication mechanism? Formation of carbocation. Formation of carbocation. Clear? Right. See, I am following two different paths. This is first path, and this is second path. Second path. What is first path? What is second path? Let us see. In the first path, I am shifting this bond towards right hand side double bonded carbon, right left. Okay. Then just to get a concept easily, give the numbering. Give the numbering. In the first path, what I am doing, this is Roman number 1. First path. We are shifting the pi bond towards which carbon? First carbon. Then first carbon gets positive or negative charge. First carbon gets which charge? Positive or negative? Negative charge. Negative. And the second carbon gets a positive charge. This is NO2 and here OH. This is first possibility. This is first possibility. Let us see second path. Shift the pi bond to second carbon, second double bonded carbon, right? Then second double bonded carbon will get negative, negative, and first carbon will get positive. Write that. NO2 and OH, right? We have two possibilities. We have two possibilities, right? We are getting two carbocations. Which carbocation is stable? Which carbocation is stable? See, take the carbocation part only. Take the carbocation part. This part only. Only carbocation part. Roman number 1 and Roman number 2. Sorry. Here, take carbocation part only. Carbocation part only. In this box, dotted box, I kept carbocation. This part, observe only this part. This part. Take this one, means like this. What is my intention? You have to focus on this part only. This is OH and this part. This is N word. Okay. Only observe this portion, this area, only this area. Which is stable carbocation, 1 or 2? Obviously 1 only. Why? Because here plus M group is present. Plus M group. Here minus M group is present. Minus M. Plus M groups increase the stability of carbocations. Minus M groups decrease the stability of carbocations. Right? That's why this path is favorable. First path is favorable, and this is not possible. This is not possible. Clear? Right. So we follow this path only. And H plus Cl negative. We are adding HCl, right? Cl negative adds 2. Carbon with positive. H plus adds to carbon with negative. Right. So this is the product. So very, very important. We are covering different concepts in the preparations. Right. Any doubt in this? Next question. Shall we go to next one? Right, next question. Next, another important question. My question is, where Cl will be added? To the first carbon or to the second carbon? Look at this, all of you. This is the answer. See the answer. Cl negative is adding to first carbon. First carbon. Let us check the mechanism. Again, I am following two parts. Give number in 1 and 2. 1 and 2. Path 1, I am shifting pi bond towards first carbon or onto the first carbon. Then what I will get? Negative charge and positive, right? Next possibility. What is another possibility? I am shifting the pi bond towards first carbon. Pi bond towards first carbon. Then, sorry, second carbon. Pi bond towards second carbon. Then second carbon will get a negative charge. I already explained in the last class. The atom which is getting the bond will get negative charge. The atom which is losing the bond will get a positive charge. Right. Here, negative and positive. I'll give you one simple question to you. In the electrophilic addition, what is the intermediate involved? What is step 1? Once open yesterday's notes, all of you. Once open yesterday's formation of carbocation. Bhakti, look at that point only. Clear? Formation of carbocation is very, very important statement. Clear? So we have to check for higher stability carbocation. Don't consider negative charge, negative repulsions. Clear? Your approach is good, but the intermediate formed in the any reaction is taken into consideration. Here, very, very important point, that is in the electrophilic addition. This is electrophilic addition, right? Carbocation is formed, so the reaction takes place in such a way that stable carbocation is involved, stable intermediate is involved. Clear? Right. In the second structure, let us consider it as a 1. It has a 1 and it has 2. I already given conditions of resonating structures, and I said to revise. Alright, where resonance is present, look at this. Oxygen with lone pair present adjacent to carbocation, resonance is present. resonance is present. This is stable carbocation. Stable carbocation. Clear? Right. So this shifting is correct. This shifting is correct. That's why Cl negative adds to first carbon according to our number. Right. So this is not possible. Not possible. And moreover, here you said negative repulsion. So that is unstable. If we consider that concept also, this is not possible here because negative repulsion takes place. But what is forming in the middle of the reaction, which intermediate is forming, we have to focus that only. Clear? Your approach also correct only, Bhakti. But just be habituated for the taking the carbocation or carbanion which is formed in the middle of the reaction. Clear? Then you will get the absolute answer. Okay, right. This is not possible, so I am adding HCl to this intermediate. Negative charge to positive, positive charge to negative. So leads to the product. Very important model questions we are doing, right? All of you don't do simple examples, normal examples. That is total waste of time and there is no use for you. Clear? Practice tough questions. So we completed preparations of alkyl halides from alkenes with the help of electrophilic addition reaction. Clear? Right. Shall we go to next method, next preparation method, all of you? Right. From alkenes only, second method. From alkenes only, B, method B. Roman number 1 from alkenes. First one is addition of HX, like HCl, right, HBr, like that. Okay. By adding X2, where X is equal to halogens, fluorine, chlorine, bromine, iodine. Second method from alkenes only. CH2 double bond CH2 plus Cl2. In the presence of CCl4, carbon tetrachloride solvent. 2 chlorine atoms will be added. See, one chlorine will add from the bottom phase, another chlorine will add from the top phase. To different phases, bottom phase and top phase, like that. Clear? So this is anti-addition. Note down. Addition of halogen. Halogen means X2. Addition of halogen is anti-addition. This is anti-addition. Anti-addition means 2 chlorine atoms will be added from the opposite phases. One is bottom phase, one is top phase. Anti-addition. And I will give you one important point. Intermediate involved in this. Intermediate. Very important. Intermediate. Involved in this reaction. Cyclic halonium ion. Sometimes questions will come. Which of the following intermediate is formed in the addition of halogen to alkene? Answer is cyclic halonium ion. Right. I'll give you that structure also. If mechanism is very important, then we'll go with the complete mechanism. Clear? Otherwise, just we touch. Right? No need to discuss about brief mechanism because there is no application type questions on this. Clear? If you know what is the type of addition of halogen to alkene, remember anti-addition, that is important point. Right? Okay. I'll give you cyclic halonium ion. Halogen, chlorine, this is chlorine. Okay. This is cyclic halonium ion. Cyclic halonium, chloronium, bromonium ion. Just keep this point in our mind, that is enough. No need to waste the time on this. Clear? Second method, from alkenes only. We are doing preparations from alkenes. Right, can you give its common name? What is its common name, Bhakti? What is its common name? Its common name. Common name. Gem dihalide or vicinal dihalide? Gem or vicinal dihalide? Tell me. Vicinal dihalide. Vicinal. If two halogens are present on the adjacent carbons, that is vicinal dihalide. Okay, completed, all of you. Now we are starting very important preparation method. Okay, allylic halogenation, allylic and benzylic halogenation, right? Allylic halogenation. Once again, I'll revise what is allylic position. Allylic carbon, allylic position. Okay. sp3 carbon, sp3 carbon, which is itself attaches to sp2 hybridized carbon, is called as allylic carbon. This is allylic carbon, allylic carbon, and this position is called allylic position, allylic position, allylic carbon, allylic position. Identifying allylic position is very important. Identifying allylic position is very, very important. Clear? And this is most important question in the preparation methods. Clear? Don't neglect it. Allylic halogenation. We completed what is allylic position. What is allylic position? sp3 carbon, which is itself attaches to sp2 carbon, is called as allylic position. Okay. You tell me in this allylic position is present or not? How many allylic positions are present? I am giving the numbering. You tell me which position is called as allylic position. Which position is called allylic position? Which is allylic position? Which carbon is allylic carbon? Online students. Three and 6. This is allylic. This is also allylic. Why? Because see, first carbon is sp2, sp2 hybridized. Second carbon also sp2 hybridized. What about third carbon hybridization? Third carbon hybridization is sp3. Sixth carbon hybridization is sp3. Right? If sp3 carbon attaches to sp2 hybridized carbon, that is called as allylic carbon. So here we have two allylic positions, right? Can I call fifth carbon and fourth carbon's positions as allylic position? Can I call? No. Why? They are sp3 only, but not connected to sp2. Not connected to sp2. sp3 again connected to sp3. So these 4 and 5 positions are not allylic positions. Clear? Right. You tell me. Right. Allylic carbon, allylic position. Right. Benzylic position. Benzylic position. sp3 carbon which is attached to benzene ring. sp3 carbon which is attached to benzene ring directly. sp3 carbon which is attached to benzene ring is called as benzylic carbon. Benzylic carbon. benzylic carbon, and the position is called as benzylic position. Benzylic position. Allylic and benzylic positions. I am giving numbering, you tell me which is benzylic position. Here, this is benzylic position. Okay. Benzylic means sp3 hybridized carbon which is directly connected to benzene ring is called as benzylic position. See, we completed allylic positions and we completed benzylic positions, right? Some reagents are there, particularly they release halogens at allylic positions and at benzylic positions. Clear? You should remember that reagents. Okay, they release or they attach the halogens at allylic and benzylic positions, right? Look at this, all of you. NBS, first reagent. You can keep adding reagents which release halogens at allylic positions or benzylic positions. Reagents which release halogens at allylic and benzylic positions. NBS reagent, N-bromo succinamide. N-bromo succinamide. First reagent. What is its role? It attaches bromine at allylic position. It attaches bromine at benzylic positions. Clear? Right. NBS. Second one, SO2Cl2. Heat or Hn. This is sulfuryl chloride. Sulfuryl chloride. Its role also releases chlorine in the allylic and benzylic position. Third reagent, Cl2 or Br2. See the temperature condition 400 to 500. Don't neglect this condition. Temperature condition also very important. See, based on the temperature, the product will change. You know, if I didn't mention the temperature, then product will be different. If I mention the temperature, product will be different. Clear? So temperature rule is very important. Clear? Cl2 with temperature and without temperature acts differently. Clear? Right. So these are the most important reagents which are used to do allylic halogenations. Allylic halogenations. NBS. Let us see the structure of NBS. Okay, you should have some idea about the structure of NBS. Okay, reason is there. You know, succinic acid. Oh my, such good apple code. In the first year I given to you. Succinic acid in the nomenclature. Derivative of succinic acid. N-bromo succinamide. This is succinic acid part. Okay. N-bromo succinamide. You remember this NBS reagent release bromine radical. Very important. Bromine free radical. Bromine free radical. Bromine free radical is released. Bromine free radical. Okay. Don't bother about remaining part. Clear? Some students will ask, sir, what about C double bond? What about N? Okay, no need of knowing about them. Clear? Just you have to remember this point. What is the role of NBS? Just it release bromine radical, bromine free radical. That is important point here. Clear? Right. Similarly, SO2Cl2 also release Cl radical. Cl2Br2 at 400 to 500 release radical. So free radical mechanism is involved in this, right? Free radical substitution. Okay, this comes under free radical substitution. Free radical. Let us first example, very simple, very easy. Select allylic position and attach bromine there in allylic position only. Okay, H1H will comes out, but you no need to learn about byproducts. Learn like this only. How I am giving, learn like that only. Don't make the subject complicate. Clear? Already you are learning excess of reactions. Clear? Required excess of reactions only. Right. So whenever you observe NBS, what you have to do? Take bromine and put in the allylic position. Clear? Remove H from the allylic position. Remove H from the allylic position and attach Br. Trick. Remove H from allylic or even benzylic also. Allylic or benzylic. Works for benzylic also. I'll give you that example. Okay? And add bromine. If original mechanism is useful, and if we have applications based on the original mechanism, then only I'll explain original mechanism. Otherwise I cannot, because time is not sufficient. Clear? Right. Example 1 is okay for you, everybody? Example 1. Right? Example 1. Next, example 2. Example 2. NBS. I'm giving numbering 1, 2, 3. You tell me at which position 3 and 6 IH free radical is stable. What is the order of stability of free radicals? 1 degree, 2 degree, 3 degree. What is the correct order of stability of free radicals? Tertiary free radical is more stable than secondary free radical. Secondary free radical is more stable than, right. NBS, or you can use any other reagent also for allylic halogenation, like SO2Cl2, then Cl will come. When you use NBS, bromine will come. When you use SO2Cl2, Cl will come. When you use Cl2 400 degrees centigrade, chlorine will come. I'll give you that examples also. Right. I'm giving the numbering. You tell me, anybody, to which position bromine will come. You have 2 allylic positions. Sir, be correct only, no? How many allylic positions we have? How many allylic positions we have? 2 allylic positions. Third one is allylic position and the 6th one also allylic positions. Allylic position only, right? Saad, can you tell me to which position BR will come? Saad and Ubaid. To which position? Why third position? Why third position? Very good. Tertiary free radical. Tertiary free radical. See, here I'll explain the mechanism. Right. 6th one also, but the major product is this one will be the major product. You will get this one also, right? But this is minor only. Major product is this one, right? Let us see the mechanism for this. Very simple shortcut mechanism, right? This is minor. Look at the mechanism, all of you. All of you, please respond, everybody. Okay. Don't unmute your mics. Mechanism. You tell me what is the role of NBS? What I given to you. Once look at this. NBS release bromine free radical. Bromine free radical. Bromine radical will be released. Now I am taking the reactant and I am removing allylic hydrogen. Allylic hydrogen as a radical. See. Here one hydrogen will be present or not? At third carbon, at this carbon, already 3 bonds are present. 1, 2, 3. So you have to imagine one hydrogen. You have to imagine one hydrogen. See, between this hydrogen and this carbon, one electron is present, right? How bond formation takes place? By the mutual sharing of electrons, right? Electron and electron. So I wrote. This point you have to remember. At allylic position, homolytic cleavage takes place. Homolytic. Homolytic means hydrogen takes its own electron and carbon takes its own electron, right? Homolytic cleavage. We'll get radical dot radical. That is the mechanism. This is 3-degree radical. 3-degree free radical is stable. 3-degree free radical is stable. In the next step, attach Br. Okay. Got it, all of you? All of you, did you get this? Why Br is preferentially added at third carbon only? Because if you remove hydrogen at third carbon, you will get a 3-degree free radical, stable. This is stable. Okay. Got it, all of you? Srujan, are you following? Benzylic. NBS also used to do benzylic bromination, benzylic halogenation. In the benzylic position, CH2Br. Okay, bromine will come. Same mechanism. Br radical will come, and from the benzylic position, H dot will go. You will get radical here. To that radical, Br radical will add. Right? Next. Actually, you will get this type of example. This is the question. NBS. What will be the answer? I am giving the options for this question. First option. Which one will be correct? See, if you get any confusion, If you get any confusion, consider it as a CH2CH3. Now you can answer. If you get any confusion, imagine CH2 and CH2 here. Okay, CH3. What will be the answer? BRA. C is not at all possible because on the benzene ring attachment is not possible. In other reaction it is possible. I'll tell you later. See, if you attach Br at this, okay, then you will get this. But that is not possible. Why? You will get primary radical only. Here you will get CH2 dot primary radical only. That is unstable. If you remove this hydrogen, here you will get secondary radical. Secondary radical is stable, so B is possible. B is major product, right? If you remove this hydrogen and if you attach Br, that is correct. Why? Because if whenever you remove hydrogen from this H dot, you will get secondary free radical. So this is correct. Clear, everybody? All of you. Shall we go to next one? Right. See, like LBS, we can use other reagents also. Let us take some examples with other reagents. Okay, right. Sulfuryl chloride, SO2Cl2, HNu or heat, Cl2, 400 degrees centigrade, Cl2 or Br2, 400 to 500 degrees centigrade. That range we can use. Clear? You can use 400 or you can use 450 also. 400 to 500 range I given. So what is the role of SO2Cl2? Release halogen into the allylic position. Cl2 500, 400, same. Release halogen into the allylic position. So the product is CH2Cl. Clear? What is its IUPAC name? What is its IUPAC name? Can you give its IUPAC name? Its IUPAC name. Anybody? 1, 2, 3. 1, 2, 3. 3-chloropropene. 3-chloropropene. Third position chlorine is there. 3-chloropropene. 3-chloropropene. Right? Completed all of you. This is about allylic halogenation, allylic and benzylic halogenation. So all these are used for allylic and benzylic, remember that point. Okay, right. First preparation method is completed. Preparation of alkyl halides from the alkenes. Alkanes, right? Next keep second method from alkynes, preparations from alkynes. Roman number 2. Preparations of alkyl halides from alkynes. From alkynes. What is its name? What is its name? What is its name? Let us do one thing. Let us do one thing. Wait for some time. First, I'll explain Markovnikov's rule and anti-Markovnikov's rule. Then I'll go with the second method because I have to use these rules, Markovnikov's rule and anti-Markovnikov's rule. Clear? We completed preparation from alkenes. So next one subtopic, okay, one separate topic, Markovnikov's and anti-Markovnikov's rule, that is over already in the first year. But again, let us start. Next topic, Markovnikov's rule. Any idea about Markovnikov's rule? Markovnikov's rule, anti-Markovnikov's rule. So again, what is Markovnikov's rule? Tell me. The negative addition. Okay. Right. Okay, no problem. See, the negative part of the reagent or addendum adds to the carbon with less number of hydrogens. Right. The negative part of the reagent or addendum adds to the carbon with less number of hydrogens. In alkene or in alkyne, we can see this type of addition mostly in alkenes and in the alkynes. Clear? The negative part of the reagent or addendum adds to the carbon with less number of hydrogens. This is Markovnikov's rule. Right, let us start. What is negative part of HCl? What is negative part of HCl? Cl negative, right? Cl negative. This is reagent or addendum. Negative part is Cl negative. Observe these two double bonded carbons, 1 and 2. See, addition always takes place at double bonded carbons only. So we have to see the double bonded carbons only. Okay, don't take the consideration of third carbon. Clear? This is single bonded carbon. Addition do not takes place at this normal electrophilic addition. Clear? So consider these two carbons only, double bonded carbons only. Add atoms at double bonded carbons only. Clear? Between these two, first and second, which carbon is having less hydrogens? Second carbon is having less hydrogens. Lesser. Okay, less number. Or sometimes we can take 0 also. The negative part of the reagent always adds to carbon with less or 0 carbon, 0 hydrogens. Less number are 0 hydrogen. Sorry, without hydrogen also we can take into consideration. Clear? This one is having 1 hydrogen. The first carbon is having 2 hydrogens. So negative part, take the negative part of HCl, Cl negative. Cl negative adds to this one. Clear? After addition, double bond converted to single bond. Okay. Here I am adding hydrogen. So you can write this part as CH3. Clear? This is Markovnikov's rule, right? Here the difficulty is some students will get confusion in finding number of hydrogens. Clear? Here I given hydrogens directly, right? Here 2 hydrogens are appearing, here 1 hydrogen is appearing, so you can add. But if I give any other different structure, bond line structure, okay, let us see how many of you will give the answer. Give the answer for this. Apply Markovnikov's rule. First and second, where Br will be added, where H will be added. first carbon, right? All of you look at this. I am considering first carbon as pink one, pink color, representing second carbon as white. Okay, I am observing number of hydrogens around pink one, around pink. Sorry. Take pink carbon, means first one. First. 1, 1, 2, 3 and 4. Around this carbon 1, 2, 3 and 4. Already 4 bonds are present. Is there any hydrogen? No. Already its valence is completed. So first carbon is having 0 hydrogens, right? Next, second one. Around second carbon, how many bonds are present? So this side 1 bond, 1, 2, 3. Around this carbon, how many bonds are present? 3. But carbon valence is 4. So you have to imagine one hydrogen there. So imagine hydrogen here, right? Don't consider it as 2 hydrogens. 1 hydrogen is present at this. Clear? Right. Now what is the rule? Once go back. The negative part of the reagent adds to the carbon with less number or 0 number of hydrogens. Less or 0. Clear? Are you getting? Right. You see. This is not having hydrogens, means 0. So add Br negative there to this and hydrogen to this. Negative part of the reagent adds to carbon with a less number of hydrogens or 0 number. This is not having any hydrogen. At first carbon there is no hydrogen. So this will be the product. This methyl will come in the product. Methyl and Br. Additionally we are adding Br and hydrogen. Okay. Any doubt in this? Ayesha, did you get this? Markovnikov's rule. Surabhi, Vaishnavi. That is about Markovnikov's rule. Right. Next, keep getting anti-Markovnikov's rule. Anti-Markovnikov's rule. The negative part of HBr, particularly HBr only. Don't take HCl or HI or HF, only HBr. This definition works for HBr only. The negative part of HBr adds to the carbon with more number of hydrogens in the presence of peroxide. This is very important condition, peroxide. So when you observe HBr along with peroxide, then add HBr according to anti-Markovnikov's rule. Clear? This set HBr and peroxide set is mandatory. Let us see the peroxides. Examples of peroxides: sodium peroxide Na2O2, hydrogen peroxide, barium peroxide BaO2. So whenever you observe HBr along with H2O2, HBr and H2O2 both should be present. Then only we add HBr according to anti-Markovnikov's rule. Here condition is important. For example, if you have HBr without H2O2, then don't follow this. Don't follow. If you have only HBr, don't follow. When you have to follow anti-Markovnikov's, HBr along with any peroxide. Okay. The negative part of the HBr adds to the carbon with more number of hydrogens in the presence of peroxide. Let us see this example. What is the negative part of HBr? Br negative. Br negative. Okay. Got it? All of you. Anti-Marconic oxide. Obed, are you following? Obed? Vaishnavi, you? Vaishnavi. Anta okay kada? Surabhi, follow avutunnara? Sath, what about you? Bhakti, nuvu? These are basic rules, okay? Fundamental. Right. Now coming to the preparations from alkynes. Roman number 2. Preparation of alkyl halides from alkynes. First preparation method, by adding HX, where X is equal to halogen. Fluorine, chlorine, bromine, adding X. See first example, I am taking acetylene, and I am adding 2 molecules of hydrogen chloride, 2 molecules of HCl. What I am getting, look at this, CH3. I am getting gem dihalide or geminal dihalide. Very important. Gem dihalide. Halogens, 2 halogens are present on the same carbon, gem dihalide. Look at the mechanism. Mechanism means how product formation takes place. In the mechanism, what we learn, how product is forming, right? Adding first molecule, see. In the mechanism, let us take step 1, adding first HCl, We took 2 HCls, right? So let us add first HCl. How HCl dissociates into H plus and Cl negative. So Cl negative and H plus. I am adding directly Cl here and H here. HCl dissociates into H plus and Cl negative. I am adding H plus to this carbon and Cl negative to this carbon atom, right? During addition, bond multiplicity decreases. Bond multiplicity means if triple bond is present, that will become double bond. If double bond is present, that will become single bond, right? Got it? So this carbon is getting Cl. Okay. First molecule is added. First molecule is added. Adding second molecule. Adding second HCl. Take this as it is. Take this as it is. Now in this case we follow Markovnikov's rule. Why this is unsymmetrical? This is unsymmetrical alkene. Clear? So here this is symmetrical only. This carbon is having one H. This carbon also having one H. So you can add Cl negative to any one of the carbon. You can add Cl negative to this carbon, or you can add Cl negative to this carbon. Okay. But in this case we have to see the carbon with less number of hydrogens. We have to follow Markovnikov's rule, right? I am adding second one, right? Follow Markovnikov because hydrogen number is different now. Your hydrogen number is same. That's why you can add Cl negative to any carbon. Nothing will happen. But here, this carbon is having one hydrogen. This carbon is having two hydrogens. What is Markovnikov's rule? In generally, we follow Markovnikov's addition only. When we follow anti-Markovnikov, when we have HBr and H2O2. In case of HCl or HI, we follow Markovnikov only. What is Markovnikov rule? Negative part adds to carbon with less number of hydrogens. This carbon is having one hydrogen. This carbon is having two hydrogens. So add to this carbon. Okay. Sorry. Right. So what we will get? CH3. Already two hydrogens are there. You are adding one hydrogen. And during addition, what I said, if double bond is there, that will convert into single. See, this double is converting into single. So geminal dihalide or gem dihalide is formed. Okay.